Hello, and welcome to this AMETEK Land webinar. My name is Katie, and I will be your Global Spec moderator. Now I would like to introduce today's presenter. With us today is James Cross. James is the Global Industry Manager of Hydrocarbon Processing, or HPI, at AMETEK Land. To read more about James today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to James to get this webinar started. So go right ahead.
Hello everybody, thank you for joining today's webinar. My name is James Cross and the topic today is monitoring critical assets in refineries and petrochemical plants using our advanced thermal imaging technology. I'm based in the UAE and I focus on this area exclusively, but a lot of the ideas, the technologies and even applications are things which can be applied to a whole load of industries. So part of the aim today is to get you to think about different ways that you can use those thermal imaging technologies. And feel free to contact us at any time with those ideas, with those potential innovations, and that's how we learn what the market and what engineers in the various fields are looking for. So we're very keen on maintaining that feedback. At a glance, AMETEK Land has been doing temperature measurements since 1947, and really from the beginning our emphasis was on temperature accuracy using non-contact methods. So we have one of the world's leading ISO 17025 laboratories in Dronfield, Sheffield, UK. We have a team of very experienced, very smart physicists who focus on wide dynamic ranges, so we like to be able to give accurate temperatures across the whole temperature range in industry. Reliability is obviously a core focus, considering the harsh applications, the high temperatures, the low temperatures, the toxic gases, heavy dust environments that we operate in. And we use a variety of cooling media to achieve that reliability, which I'll talk a little bit about today. And then we innovate. We focus on the decarbonizing, digitalizing objectives in industry, and including having communications protocols to operate in a cloud environment, but also whilst operating in that hazardous explosion-proof certification requirement as well. And then we also focus on the after-sales. Generally speaking, in petrochemical industries, you can divide our product range, service range into four categories. And I'm obviously talking about critical asset monitoring. There's some overlap into other areas like flammable material monitoring, furnace monitoring, flare and pilot detection, and critical asset monitoring, the variety of assets that we can talk about. And so today I'm talking about technology which can be applied to even more applications, but those are kind of the four that we've found most interesting and which customers seem to be investing in the most. Just going back to basics very, very quickly, because some of the previous webinars I've done, we're talking about very high temperatures where we're in the short wave infrared and the mid wave infrared part of the electromagnetic spectrum. Today, we're really talking about long wave infrared. So that's generally in the 8 to 14 micron range. So as you can see, that's quite far from the visible range. The visible infrared range is right in the 0.4 to 0.8 micron. So that's high frequency, short waves. And that's why, for example, the human eye is responsive to infrared emissions in the very high temperatures. So we can see steel as it starts to glow at high temperatures, but we can't see it change color at low temperatures. That's why infrared cameras in that long wavelength range are very useful, because they can measure accurately temperatures of surfaces changing temperature in that low temperature range. The important concepts to understand, and these are even more important at low temperatures in some cases. So Kirchhoff's radiation law is is critical here. So a good absorber, generally speaking, a good way to think of this is that a good absorber is a good emitter. And absorption and reflection add transmission equals 1. So you can look at the reflectivity of an object and understand its absorption and therefore the amount of infrared energy that it's emitting. A good way to think of that is emissivity is 1 minus reflection. And that's important in low temperatures and the sort of objects that we're monitoring with these infrared cameras, because you can have shiny surfaces which are highly reflective, and you can have rough, dark surfaces which are highly absorptive and emissive. So again, as an object heats up, the steel radiates, or the material radiates more of its energy at lower wavelengths. Emissivity then is the ratio of the radiation emitted by the real object to the radiation emitted by a black body. So a black body is emitting all of its energy as infrared radiation, so it would have an emissivity of 1. In reality, we're working with grey bodies which emit only a portion of that radiation, and a portion of that radiation is internally reflected. That's a challenge, as you can see in the image on the bottom right-hand side. For example, the reflective metal connector, crimp, which is a chrome material, has a very low emissivity and a high reflectivity. And the isolation has a very high emissivity and a low reflectivity. So if we don't correct for those temperatures, if we don't apply our emissivity factor, those temperatures in fact look very, very different. One temperature with a high emissivity looks like 83 degrees Celsius, and the temperature and the area with the high reflectivity is 36 degrees Celsius. That's a huge difference. That's not a realistic temperature difference. That's explained by emissivity and reflectivity. And you can imagine if you're going around a refinery or a petrochemical plant and you don't understand these concepts and you start measuring reflective surfaces with an infrared camera without applying these emissivity corrections, then you can start to think that things are really a lot hotter than they are, or a lot colder than they are. So these are really important concepts. The emissivity changes depending on material, surface, temperature, and angle. Angle is a really critical one as well, because if we're measuring cylindrical objects, spherical objects, for example, pipelines, and we don't have the correct viewing angle, or we don't have a suitable viewing angle, the emissivity of that target effectively drops as well. So we can also have a large error in our temperature measurement. So we start to measure surfaces with a much lower emissivity than we think we might be measuring. So the spectral ranges we operate in, like I said, at Amatec Land is the near infrared, the mid-wave infrared, and the long-wave infrared. Mostly talking about applications today from ambient temperatures up to 1,000 degrees, but in reality, when we're doing critical asset monitoring and surface monitoring, we're talking about 0 degrees Celsius up to, say, 300 to 400. Most applications that we work with in this area, really the priority is to know whether you're over a temperature. The accuracy requirement once you're over that temperature is not really critical. Most of our customers just want to know if they're operating within the correct window, and if they're over the window, it's almost like a switch point, and an alarm is required, and then an investigation can be done. The camera that we're talking about and we're very proud of is the LWIR 640 EX. EX meaning that this is certified when used with our EXSH housing for hazardous areas in Zone 1 or Zone 2. It's highly accurate. It's smart, meaning that it has capabilities to integrate with plant DCSs, variety of communications protocols. It has on-board regions of interest and I/O, meaning that you can set regions of interest in the camera and hardwire that I/O from the camera to whatever it is you want to communicate with. That might be an ignition panel, it might be a server, it might be instrumentation in the field. And that means that we can install the camera, communicate directly with that equipment without going through additional switches. So it's quite a nice advantage when you're working in areas where there's no infrastructure existing already, or little infrastructure existing already. And then autonomous functionality based on the latest detector. So regions of interest, just to explain what a region of interest is quickly in our system, you can see the image in the screen. So we've created 3 regions of interest, 1, 2, and 3. And what we can do with those regions of interest in the camera's web server is analyze the minimum temperature in that, the maximum temperature, and the average temperature in each of those regions of interest. And then we can output those values using those onboard I/O. So that means we've got 3 I/O outputs. We've got 3 I/O on the camera. We've got a 0 to 4 to 20 milliamp output on the first on the first terminal. We've got a 0 or 4 to 20 milliamp output on the second terminal, or a relay output. And then the third terminal, we can use a 4 to 20 milliamp input, or a digital input, or a relay output. So it's pretty versatile in terms of what you can do with those regions of interest. So those regions of interest are analyzing and recording the temperature values in the scene, and then the camera itself can be configured to output these variety of options. Typical system architecture, so you would have the camera communicating to a power supply unit, which is then going to a control room unit, which is then going to a standard workstation with our asset monitoring software. And I'll talk a little bit more about the asset monitoring software later. So when you've got multiple cameras communicating with the asset monitoring software, you wouldn't necessarily also be using the onboard I/O. You can use the communications on the camera, so you would have that wired via Ethernet from the camera to the junction box to the control room unit, and then you can have fiber optic connection from the control room unit to the server, and then the software does the advanced data collection and monitoring. So let's talk about some applications. The first application I wanted to talk about is measuring cold collector temperatures. So that can incorporate monitoring the pigtail surface, the manifold, the main header of really any type of fired heater, but essentially the most interest we've seen in this area is from steam methane reformers, where you have that very high gas exit temperature, therefore having high tube skin temperatures, and then refractory lined pipework and main headers or outlet manifolds exiting that furnace. So because of those high temperatures and that temperature gradient, the monitoring of these surfaces is actually quite critical, and in some cases as critical as measuring the internal surface temperatures of the tube. So interestingly, if you have data from the skin temperature on the inside of the furnace, and you're measuring the surface temperatures of the outlet manifold, pigtails, and the main header, you actually get really good information about what's happening to that gas as it exits the furnace, and certainly more information than you would get from a common furnace design where you're getting a limited amount of gas exit temperature data. One thing we've done with a few of our customers is install thermal imaging cameras beneath the furnace, in between those tube rows, and then our thermal imaging camera is collecting and archiving, alarming that data to alert the operators if there's a temperature excursion in that area. So we've noticed an increase, especially in the Middle East here, in interest for this type of system. So that's something which is an interesting trend. On the hot collectors, you obviously can't use a camera which is outside the furnace to do this. So what we've done actually with our boroscope system, so we can put our camera on the end of a boroscope, which goes into the furnace, and it can measure the temperatures of those tubes or manifold systems which are inside the furnace. So that's been an interesting development as well, that trend to monitor coal collectors and hot collectors, which we're very interested in. And you can see this is a nice table from the AIGA document on the mechanical integrity of syngas outlet systems. So you can see that the various issues with hot outlet systems and cold outlet systems and those common components, they really are susceptible to different failure mechanisms. So metal dusting, thermal aging, thermal fatigue, creep, excessive stress, stress-related cracking, and more. So monitoring of these is probably quite an underappreciated area of these high temperature processes. It's done currently with kind of periodic inspection. It's done with thermal sensitive paints. And the limitations of that is that it's not being continuously monitored or trended. And once you do start to trend those things, you can start to see the relationships between those outlet temperatures and the tube temperatures. I think it's quite a useful data set to have for these operators. If you have things like temperature fluctuations inside the reformer tube or inside the furnace, so poor flue gas distribution inside the furnace, those exit temperatures can fluctuate significantly and they can swing significantly, which causes that type of thermal fatigue and potentially causes the type of damage that you can see on the bottom right. Vessels, high temperature gasifiers are another area which we focus on with this type of technology in refineries. So in the event of refractory damage in these vessels, and they operate at a variety of temperatures over 400 to 500 degrees C, right up to 1300, depending on the application. That's flue gas temperatures. If that refractory is damaged, then those hot gases push into the gaps of the refractory lining, and then that damage increases hour by hour, and it can become a relatively catastrophic incident if that's not detected. So if it's not recognised early, it can cause further breakdown and that catastrophic failure and damage to the plant, injury to personnel, or an unplanned shutdown. The current monitoring methods for that include sensor cable, so that can be fibre optic, thermistors, it can be thermocouples, that measure single points. So they're wrapped around the vessels, but they measure only a single point. So you've got large gaps in between those points, which could be the area that you have a seriously high temperature. The infrared thermal imagers have been increasingly adopted on these gasifiers, but also retrofitted to existing plants. So we work with the licensors of new technology, but also with the end users to install these thermal imagers around the gasifiers. They're quite difficult applications in a lot of cases. They're very crowded areas, and they're quite congested by scaffolding, by additional levels, by walkways, and that means that sometimes we need quite a few cameras to cover these gasifiers, but the benefits are still there in terms of coverage which you receive. So the existing methods, you don't have the detection of early refractory damage. The average temperature measurement over a large area doesn't really give you the type of resolution that you get otherwise with the thermal imaging system. Tubes and sensor cable can lose contact with the vessel shell, so they're measuring ambient air and not the actual shell temperatures. Mechanical damage during installation can cause false hotspots, so you get false alarms and you start shutting down equipment that you don't need to. Operational lifetime is relatively limited, especially in hot environments like here in the Middle East. And then typically sensor cable needs to be replaced after a few years of operation. Thermal sensitive paints are used regularly. One issue that a couple of our customers have talked about with those is that the time required to apply and reapply those is actually pretty extended during time-sensitive shutdowns. One unfortunate incident we were involved with this quite a few years ago now. Was in Terre Haute, I think that's how it's pronounced, in Indiana. So the vessel expanded, which caused a leak at the flange, and then when the operators were sent to tighten the bolts on that flange, an explosion occurred, and tragically that killed both people. And then one of the corrective measures after the investigation into that incident was to ensure that thermal imaging systems were added to the monitoring automated monitoring system, so that type of incident was. So infrared allows early recognition of possible damage. We can actually increase the refractory life and maintenance periods because we're adjusting the variables that we can adjust to ensure that you don't have hotspots. And when you don't have hotspots, you don't get that fatigue on particular areas of the shell or of the refractory. We can avoid catastrophic failure and damage to the plant, protecting those personnel from incidents, reducing shutdowns, maintenance and material costs. The thermal imager is non-intrusive, so it's easy to install, and it sits outside the furnace, and it's generally in hot environments cooled. The lens is purged, so the camera itself is sitting in very comfortable conditions, so the lifetime is 10 plus years typically. You get very accurate single temperature measurements, so we can get within 2% or 2 degrees C of the true surface temperature. Again, understanding the concepts of emissivity and reflectivity, we can use that experience to make sure the values are accurate. And hotspot detection, alarming using the advanced asset monitoring software, and then we can store and trend that historical data for any investigation. So this is a typical installation on a gasifier. So we target those two critical areas, so the dome area and then the cone area. The good thing about that is that there are generally walkways and handrails, poles that we can mount our equipment to, or if we want to put it on the walkway, we can. And then we've got a variety of accessories to mount those cameras, and then we can put additional cameras on the sidewalls as well. So we monitor those areas, in this case with 8 cameras, and then that data is fed into the asset monitoring system. So the asset monitoring system on the right-hand side is collecting the temperature values from those 8 cameras and then automatically zoning that data and recording that data by zone. So an overview of all the cameras installed, grouped by those zones or areas for 24/7 continuous monitoring, trending, logging of up to 16 cameras. We do have applications where there are slightly more than that, but generally speaking, the standard software works with 16 cameras. And then you've got a customized overview, so we can tweak the software, import images, 3D files, and customize that software according to the specific application. And the alarms, active and historical system statuses are logged to the database, monitored continuously. The trend graph shows the historical temperatures and trends for each. So we're continuously also monitoring the camera's health. So there's temperature sensors inside the camera itself to make sure that the cooling media is being supplied effectively. The camera itself is installed in the jacket, and we can install that in a 2-skin EX housing where we can supply water cooling. Some customers have supplied vortex cooled air, and then we also keep that lens purged as well to ensure that it stays clear. Flammable material, I mentioned briefly in the beginning, is another area which we focus on. And in petcoke facilities, in sulfur storage facilities, and other flammable materials, we can use the same camera inside the same housing. So that's dedicated IEC dust certified housings with window cleaning, which is incredibly important in these type of areas, purges, and then connected via a dust certified junction box as well. So we can install those intervals on elevated walkways to monitor the surface temperatures of those stored materials, and that gives early warnings of the development of spontaneous combustion. And we've seen examples actually where a customer during the commissioning phase of this type of system will say to us, your camera is not working. It's telling us that there are hotspots in areas that there are clearly not hotspots in. And the sensitivity of the device is such that it can see hotspots that are really, really far beneath the surface. And you get that thermal conduction through the surface because, going back to emissivity, these types of materials that are highly flammable are generally very good emitters. So you get very good thermal conductivity from a hotspot in the bottom of one of these storage facilities right up to the top. And the sensitivity of the camera means that we can see those hotspots really as you get a small increase in the temperatures. And in a few cases, we've detected really, really significant hotspots that may have otherwise gone undetected and could have caused pretty serious damage to the facility. So that's an example of where high sensitivity, high resolution, high accuracy cameras inside these explosion-proof, dust-proof housings is a really valuable addition to one of those facilities. So thank you for attending the webinar. I hope you had a good insight into some of the applications that we work on, the camera that we're employing for these applications, and some of the basic concepts in infrared technology. I collected a few questions from some of our partners prior to the webinar, so I'll go through those now. One question was on the possibility of pan and tilt integration to the camera, and this is possible, something we don't currently employ in the software ourselves, but we do supply the accessory kit for the camera in the hazardous area or the non-hazardous area. So that would be something which would need to be added as a bolt onto the system, and we can obviously quote that through our engineering team. Another question I had was on the cooling media flow. So that's something we do specify in the manual. Generally, you can use around 100 litres a minute on the LWIR EX application. So where that might be pointed up, for example, or when it's in a particularly dusty environment, you might need slightly more than 100 litres a minute. We actually test, when we test the lens purging, we actually ensure that flow, we ensure that we know the flow required to actually clean the lens if it does become contaminated. So if you have an interruption of the window cleaning purge, we like to know the flow needed to clean any contamination of that surface. So that's generally 250 litres a minute. Again, that's quite a large flow, but that's not required necessarily all the time. You could pulse that, or you could have that on a solenoid, or you could have that as a manual valve if you just want to periodically clean that lens. Another question I had was on viewing distance. So what's the camera's capability to view at long ranges? So we know a lot about this from the flare monitoring, pilot flame monitoring, because we have a 640 by 480 pixel camera, and we know that at long distances you start to the pixel range, or the spot size of those pixels starts to cover quite large areas. So once you get to kind of 300 to 400 meters on a 6-degree lens, you do start to lose some resolution on those targets which are a long distance away, and then you start to measure the average temperature of a larger area. So generally speaking, we engineer the system according to the design requirements. So on a gasifier, you need a wide-angle lens because you're measuring surfaces at a close distance. On a flare or pilot flame monitoring system, you're measuring distances up to 350 meters. So you need a narrow field of view lens so that you've got that high resolution on the target, which is further away. Physically speaking, infrared physics is not really dependent on distance. The only thing that we need to consider is what might be filtering that infrared radiation between the target and the camera, be it dust or steam. So we just look at the application on a case-by-case basis and design the solution according to those. If there's any further questions, I'm happy to take those offline, and I'm happy to respond to people. You saw my email at the start of the presentation. And thank you for attending, and looking forward to exploring more applications with you as they come up. Thank you very much.
James, thank you so much for that great presentation. For all of our attendees, if you have a question for us today, please go ahead and enter it into the Q&A window and hit submit. James will get back to you with an answer. You're also going to be receiving an email from us with a link to the on-demand version of this presentation. You will be able to come back and watch this again or share it with colleagues. Lastly, please take a moment to complete a survey which will appear on your screen at the end of this webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you so much for taking time to attend this webinar event. Take care, and we will speak with you soon.